Okay, so I'm going to take you on a journey, on a little journey, and I'm going to talk to you about how do we observe Earth from space. Let me tell you a little bit. So I'm a physicist, and I study physics, and at the end of the university, I thought, well, I want to do research. And I had to decide between, and so everybody, the cool people in physics, they do particle physics. That's what it is. That's some of my best friends. And I thought, well, they think are the cool people. That's what it comes, after. And I thought, well, I want to do research, and I thought, Earth science has a lot of good questions to be answered, and we don't know so much about the Earth. So I thought, well, I'm going to start working in Earth science. And at first, it was kind of tough because, in Italy, when you study physics, you do a lot of math, and everything is, goes in a box. And then when you have to deal with data, in Earth science data, things don't work usually, and then you cannot say the data are wrong. You have to understand, oh, what do I do, why they do this, or what are my assumptions. And so at the end, I thought, well, and it took me a while to get used, but then I found that I have way more fun problem than I think my particle physicist, especially because, I thought, now particle physics become like astrophysics because we cannot build, accelerometer bigger than some. And because in Earth science, we are in a great time to make discovery. And why, in some field, you need really a huge team to make big improvement in the state of the knowledge. Turns out that in Earth science, because there are so many things that we don't know, and climate change helped us. Things are changing much faster and nowhere, how we were expecting. And so I think it's a very exciting field to be working in. So yes, great. Okay, so I am going to talk about, how do we weigh changes in water and ice from space. And I'm going to talk about, first, I'm going to drive you to what, how we observe changing in land ice sheets, and glacier and ice caps. And then I'm going to talk to you about regional sea level. We care about the glacier and the ice sheets because I'm a scientist. I like to solve the science question. But turns out that what we're doing is way more, has much bigger impact than when, I started to work on this, topic 20 years ago, because things are changing fast and glaciers are melting faster than we expected, and they are increasing sea level, and this is affecting population. And so that's, then I'm going to talk also about how we can use satellite to measure terrestrial water storage. And again, this is very important because, has an implication for drought. And, and so then I'm going to try to summarize, and along the talk, I'm just going to try to point out why do we care about things, not just for the science, but, and I think teaching has done this to me, and talking to people, I have to think, why do we care and what are the applications? And I think that, again, climate science, earth science, is a great opportunity for having good science questions, but also is a great opportunity to understand, for young generation, because there is a combination of a lot of different opportunities. Okay, so first, we are in a golden age for remote sensing data. So these are some of the satellites that are orbiting around our planet, and they are observing our planet, and they are measuring a lot of different aspects. And I'm going to talk to you today about one satellite that is called GRACE, but we have all those observations. They are coming online. They are publicly available. Companies are starting to use, this data. And so what is exciting is that now, even in earth science, we get students, they're told, before they finish their PhD by company, and they make some great offer to them because, they don't just learn, to study the planet, but they learn to deal with big data. They learn to deal, and they know how to use the satellite data they are used, in different companies. Again, Walmart, has, used satellite data to check how much the parking lot are full, and so on and so forth. Okay, so here I'm going to talk to you about this mission. It's called GRACE, Gravity Recovery and Climate Experiment. And the science that used this data is time variable gravity. And really, before this mission was launched, this discipline did not exist. So it's a very good mission, cool mission for a physicist because, you have two satellites that are orbiting on free fall, in the atmosphere, and they are like a distance, about a few hundred kilometers one from the other. And what they do, they are attracted by the gravity field of the Earth. And so what happened, so the gravitational force, I imagine, everybody remember, the apple that falls on land is the attraction between two bodies. And so what happened, the satellite is on free fall, and when it's closer to more mass, let's say a mountain, accelerate. And so the distance between the two satellites become larger. And then the second satellite become closer and accelerate, and so the distance become. And so what happened is that, measuring those changes in distance, we are able to monitor the changes of the mass that cause those changes. And how do we measure those changes in distance? We are measuring using a microwave link. So it's a K-band wind, and we can measure the change in distance better than 1 micrometer per second. So a micrometer is like the size of your hair, so it's better than, and this again, there are two satellites in space. And, and this is pretty, it's pretty cool. And then with each satellite has some accelerometer, so we remove everything that is not related to the mass, of the Earth. And we can get this picture, we know the position of what is the gravity field. And so on the top right, those are like the two satellites. They used to be called Tom and Jerry. And here, they really are. And here, this is an image of the last, when they were going down. The mission ended at the end, in 2017, and now we have actually a follow-on mission. This is a picture that shows the satellite orbiting on top of our head. And the cool things, and I'm going to just mention this, about the GRACE follow-on mission is a repeat of the GRACE mission, but has a laser also on board, and this, I'm going to say this for the physicists, is the first time the laser flew in space. It was supposed to be flying with the LISA mission, and the LISA mission was canceled. And so we have a laser, so we have the microwave link that measures the distance between the satellite, but we also have, a laser signal that, basically is, you have two holes in the two spacecraft. They're about, the size of a coin, and the satellite is about a few hundred kilometers apart, and you can just, and it's working very well, and they can provide much more accurate estimate of the change in distance and improve the resolution and the accuracy of the satellite. Okay, so, oops, I gave it up. So what do we see? So we are measuring the gravity field of the Earth, we are measuring the mass change, and we are measuring monthly changes. So what signal changes from one month to the other? And I kind of give it away showing this video. If you think about what are the things that they change, any idea? Rain, exactly, water storage. The mountain is still there, if we look at changes. So this is a movie that shows you the monthly mass change. This is like for, from the satellite. And what the satellites see, you can imagine the resolution. You have a disk that's about 300 kilometer radius, and you can see the change in water in mass equivalent to changing the, having 1 centimeter of water uniformly distributed on the disk. Okay, and so on land, the biggest signal is really water storage in the river basin. What we do also, we remove the atmospheric mass distribution. The atmospheric has a big mass. We know that well enough, and is removed using a global circulation model. And it turns out that we can do it to match this accuracy. And so here, what you see, you can see the monsoon cycle over India. How it changes season. And I don't know where's my laser. You can see the water cycle in the Amazon, and again, from a satellite. Now, I'm going to show you, okay, this was if we look at the seasonal variability. Now, we can also look at what is the mean mass change during the period. So if we look at the mean mass change during the period of the mission, which is between 2002 and 2016, and we plotted, what do you see? Do you recognize signal? So what do you see? So, and actually, I wanted you to notice that the scale is skewed. So it's saturated. This is -8. And we like to measure the change in mass when we look at map in centimeter of water equivalent. Just we think, how much would be the mass. So we have some signal, some very, purple. Purple is negative. Red is positive. And here we have about, 3.5 centimeter. And as you see, clearly, the two places where you have very big mean mass losses are the ice sheet, Greenland and Antarctica. And specifically, we have two regions, okay? They are really, and then do you see anything else? What is this signal, for example, in Antarctica? Turns out the Antarctica is like, this is like a big snowfall event. Antarctica is very wide. And so during the period, we had like a lot of precipitation, and we can observe that. But also, do you see any glaciers? Can you find any glacier? The glaciers are smaller respect to the ice sheet. We're going to look at them after. You can see the signal of Alaska, for example, here. Okay? So we can see those changing from space. And now I'm going to show you some application how we can use this data to look at the ice sheets. And so those are like two. So what we can do, we can look at the ice sheet, and the top are showing you basically is like we cannot look at how much the mass there is on the ice, but we can see how much the mass is changing from one month to the other. And so what we're seeing here, let me start. There we go. Okay, so it's basically like we're putting the ice on a scale, and we're going to see. And if we look at Greenland here again, and then it's relative, to the mean. So that 0 is really the mean. So we remove the mean field because we wanted to change it. And then you see in Greenland, the mass goes down, goes up. And if you go check, it goes down in summer. It goes up in winter. We have an increase in precipitation. It goes down, it goes up. This is a very nice seasonal cycle. If you go look what happened here, well, we go check here. In 2012 was a super warm here, exceptional melting, and sure enough, we are seeing it. So we do some check to check and overall, you see that there is a mass change. The mass changes, more. We have an up and down of the season, but overall, we have a lot of mass, so which means that a lot of ice got dumped in the ocean, and it melts in the ocean. So what we find what we call the mean mass change, what is, on average, if we want to say for year, and we find about 265 gigaton, and I'm going to tell you about gigaton. And then also, we find that there is an acceleration. And the meaning of the acceleration is important because it tells us that we're not losing. So the ice sheet is not melting the same amount every year, but every year is melting a little bit more, which makes that we should be a little bit more careful about what's going to happen and what is going to be the impact. And so a gigaton, so when we look at the ice sheet and mass, we like to think in terms of gigaton. And basically, to have an idea what is a gigaton, all LA County in one year, including water to irrigate, water for heavy infrastructure, use about 1 gigaton of water. So this is how much, if you do an average, the Greenland ice sheet is pouring in the ocean every year. So it's a big number. It's a lot of ice, and it's a lot. Now let's move to Antarctica. And here we have the same thing. If you look, it's very different how Antarctica. So first, Antarctica is way broader than Greenland. It's about 64 meter, 6 meter of sea level equivalent, and Greenland is about less than 10. But what you see, there is not a very clear seasonal variability there. Still up and down, but we can still see, that there is the mass is decreasing overall, and here too, the mass is accelerating. Okay, so those are just to give you an idea, what, there is a lot of progress that's been made in the past decade about what we understand about the ice sheet. So do you know what is an IPCC report? So every few years, this is like a United Nations sponsor, but there is a big assessment and to understand what is the status, what do we know about climate, and what are the things, and there is a summary that is provided to policymakers because there are decisions to be made, in function of how climate is changing. So in 2001, which is relatively, yesterday, the IPCC will say, well, we don't know what's going to happen to the ice sheets, and potentially the ice sheet may be growing because with the increase in temperature, you're going to have increase in precipitation in the interior, and so this can overcome. And so if you think, now we are in 2019, but already the last report was the first one in which we say, okay, we're seeing both ice sheets losing mass and melting in the ocean. On the bottom here, I'm going to show you, those are two movies, and they show you we can also look at how the mass, this is how the cumulative mass change from 2002 to the end of the mission. And what you see in Greenland, the mass loss, which in this case is red, is spreading. And at the end of this time, we're seeing that more and more of the Greenland ice sheet is losing mass. And in Antarctica, on the other hand, you see there are like some specific region where the changes are more evident. There are West Antarctica, and they're like the peninsula, and then there are some region in East Antarctica. So, you know, and then again, this is like from using satellite data. Okay, so what we can look, again, I'm going to show you some, oh, too fast. Okay, so this is the mean mass loss during 2002 and 2016, and this is like go back to, you know, this is like the mean, and the movie show the accumulated effect, but if we want to look at, you know, how it spread, you can see that most of the Greenland ice sheets is losing mass across all, you know, area, while in Antarctica, there are like a few regions where the changes are occurring. You know, you have the Antarctic Peninsula, the Amundsen Sea sector, and then, you know, these two areas, Totem Moss Frost, and Victoria Land, Wilkins Land, and Quimor Land. This was the area where you saw the increase in mass because of the precipitation. And if you want to look at the acceleration, again, what are the areas that control the fact that the mass is increasing, the mass loss in time? Those areas you can see in Greenland, most is coming from the west, you know, region, and in Antarctica, mostly is coming from the West Antarctica, and there is like an area in East Antarctica. They are very limited. Okay, so we care about ice sheet again because they are very cool. Well, because I'm a scientist and like. We don't understand so much about the ice sheet, by the way, because, you know, well, it's not that we don't understand. We can say that they're very remote, and now we start to have a lot of satellite data to monitoring them. But another very important result from the GRACE data is to be able to measure the mass loss of glacier and ice caps. And this is a plot that shows you, okay, so this is the location of the world glacier ice cap. In the world, there are like more than 150,000 glaciers, and more than that. You know, there are like so many glaciers. The ice sheets are very important. They're going to affect sea level. You know, glaciers are very important because they affect sea level, but also they are going to be key for economical resources for area where you have glacier. There's tourism. There's like electrical power. You know, there's power by, you know, hydroelectric and by the glacier. They are providing. They're also very important for the population. They provide water resources. So, and up to now, it's been quite hard to measure what happened with this glacier because they're like very remote conditions. We had like some point observation, or some spread observation, then we extrapolated. And so the nice thing about, you know, the satellite is that here is a map that shows you the mean change of the glacier. You can see bigger signal coming from, you know, red from the Canadian archipelago. We see Alaska, we see Patagonia, you know, Iceland and Svalbard. This is the high mountain Asia. And if we sum up all, you know, the mass loss, how much is the mass change from the glacier, we can get this curve. And we have about, you know, 238 gigaton. So it's a big signal. And also the glaciers are showing an increase in mass with time. So they are melting, and they are melting, you know. So we wanted to do a little bit more. We wanted to look, okay, so that's important because you want to see, okay, what is overall the contribution. But can we look at what are the glaciers that are changing more? And so this is like, those are a plot. Turns out that most of this mass loss from the glacier come from 7 regions. And those 7 regions are the Canadian archipelago, you know, which is like in pole position here, the one that, you know, is melting faster. And you can see, you know, and then we have Alaska, the southern Andes here, mostly driven by Patagonia, northern southern Patagonia ice field. Iceland is changing, and again, you can see a lot of interannual variability. The Russian Arctic, those are like the 3 areas of the Russian Arctic. High mountain Asia, the high mountain Asia, and there are different regions, and Svalbard. So you can see there are some of those regions have an increase in mass with time. Some have a very, you know, big interannual variability. And so, but, you know, the idea is that those are the ones that contribute more to the changes. And some of the region, you know, for example, we are funded on a project in high mountain Asia. This is a very highly populated region. And so the fate of the glacier is very important for the population. And it turns out that it's important for all of us because the 2 main issue, you know, or a cause, you know, for global security are availability of water and displacement of population. And so if this region that is very populated, if the glaciers are going to disappear and we're not going to have those water resources available anymore, that's going to be a problem not just for them, but for everybody. Anyway, so I'm going to just go back. So then let's put everything together. And this is like, so if we want to look, if we put together all this ice that is melted and it goes in sea level, and here we have like Greenland on the left, which I don't know where, and the Antarctica and the glacier, and we sum them up, we can get what is the mean, mass loss, and we can convert it, in sea level contribution, and we find that is a sea level equivalent. If we get all this mass and we spread it uniformly, on the ocean, we find that this will raise sea level by 1.7 millimeter a year, on average, and then we find that there is like a small acceleration, so increase in mass, with time due to the glacier. And if we look at the total sea level, so how much we observe sea level, using satellite data, and the total sea level, what makes sea level change on top of putting ice and water in the ocean? What else if sea level is changing? Thermal expansion. That's what you, I really, okay, and so this is like, so the missing portion is due to thermal expansion. But if we just gonna sum up this, and we look at the, what is like the increase in mass from the ice, we have about 350 gigaton, again, per decade, so if we look at every year, it's small, but if we look at which, and if we project this, we're gonna get to about 80 centimeter of sea level by 2100, which is the big thing, because that has a lot of implication for a lot of like coastal region, and I'm going to just mention some of them later. So I want to talk to you now a little bit. So one of the things, so the first, and when we look at science, I think then the beauty about being, I think, a professor at the university, we have freedom of move, in direction where the science question take us. So we, first we started to wanting to understand the ice sheet and we do work, but then it's like how those changes are affecting sea level and how they're affecting regional pattern of sea level. So that sea level, if you think about sea level, do you think sea level rise uniformly everywhere around the globe? So what are the things that make sea level change, not uniformly? So no, it doesn't rise uniformly. What are the things that make sea level change not uniformly? Which might, when you look at sea level, what are like things that you can think about?
One of the things that has been in a lot of the analysis is the Earth's crust. When the ice melts, the Earth...
you steal my cue. Yes, I'm going to talk about that. That's great. Exactly. So that stornados is a big part, and then also you have like again thermal expansion. You have like dynamic of the ocean. You have tides. Okay, but I'm going to talk to you about the effect of what is the regional sea level that is, a change that is associated to the fact that the ice sheet and the glacier are melting. And I'm going to, so I have this is the top equation, and I'm going to try to go. So if we look at change in regional sea level change, we can divide it into pieces. We can, what we call like, it's called the static sea level. It's a scary word, but and the dynamic sea level. The dynamic sea level is everything is related to ocean circulation. So, you have tides, you have like changing of the currents, you have like a lot of changes, on top, again, redistribution of mass. And then is what we call the static. And the reason why we call it static is because it's related to the solid Earth, pretty much, And it turns out that it's less static than what we thought. But it's basically related to gravitational field changes and to geoid changes. Geoid is basically, the surface around the Earth where you have a constant, potential. And I guess I went with too much math. So when we look at those gravitational changes, they're like two pieces. So you have what is called, and again, we're looking at changes. So, clearly we have change, in sea level. They are driven by the topography of the Earth. But what we have what is called glacial isostatic adjustment. So the Earth, which seems pretty sturdy, is still responding, on the other hand, is a viscoelastic fluid, which means that respond to the fact that if you remove a load, as a very long-term, response, it's a very long-term response to those changes. And so during after the last glacial maximum, we remove a lot of ice from the northern hemisphere. And so now the Earth is still responding. It's a little bit like if you sit on the couch, and you are like on a comfy leather couch, and then you get up. So when you sit, you have like two little bulge, around where you sit, and then you get up, and the couch doesn't look that good because you have the bulge, and then you have a big hole. And then if you wait, it's gonna get flat after a while. So the Earth, and that depends how soft and what is in your pillow, okay? And so that is what, we just say is like the viscosity. So the Earth is still responding to those changes, and those, what is the glacial isostatic adjustment has very, very long scale. So depending on how, again, soft is your pillow, what is the viscosity, we say you can have, but it's like constant. You have like the same change at the scale of, 100 years usually. And then there is another response, which is an elastic response. Well, it turns out that despite the Earth seems pretty sturdy, as an elastic response. So if we remove a lot of mass, immediately responds and rebound. And so what happened is that, and I'm just going to show here. So, and that happened with the ice sheet. If we remove a lot, so now we're removing so much ice, where the ice sheets are, where the glacier, that we can measure the response of the crust. And what happened here, if here is the ice sheet, we're going to have we remove ice, and so here the crust is going to uplift, is going to go up, and immediately, it's like we remove away, and there is like an immediate response. And then far, what's going to happen, you're going to have you're just going to have then the sea level is going to be less attracted because there is less mass, so it's going down. And also you have a change, in the near field. And in the far field, you're going to have the response is going to level down. So what's going to happen? And it's slightly going to rise, okay, the sea level. So if we measure what you call relative sea level, which is the sea level change relative to the crust, okay, so to the bottom of the ocean, we can see if we keep, so the elastic response, if I just remove a lot of mass and I don't do anything else, that's it, stops, occur once, and then it's going to level out. But because those ice sheets are a very specific, position, and they keep losing mass, we're just doing this over and over. And so they're going to have a very clear signature. That's like that. So what we can see, and this is pretty amazing. We knew the theory about this, but actually last year, this is some work that we did with a survey. We were able, of mine, to observe those changes. We were able to observe what is called, they're called the sea level fingerprint. And it's sea level fingerprint because the pattern, okay, of this is just defined by some elastic parameter that define the elastic response of the Earth. Okay, the theory was like very well known, but it was never observed, and we were able to observe it, and that was, quite exciting. But there are specific patterns depending of, and if you think of water, like again, the rapid change are consistent on land. It's like land distribution, water distribution on land, and again, and then over the ocean. And so here I'm going to show you. This is a pattern. So this is a movie, and here is like what are the sea level fingerprints. So this is like, after I remove, we lost all this ice mass, which on average is like those 65 gigaton for 14 years. And we're going to look what is going to be the elastic response, okay, caused by Greenland. This is what we got. We got the sea level is going to be going down again because of the crust, okay, change. Close, we call the near field, and it's going to raise when we get away. And Antarctica, the same thing. So you see the signature. And if you look at what I call the land water mass, basically is land water and the glaciers, you can see that you have a pattern around the glacier that you saw in red before. They're the one that are losing more mass. So if we sum up all of this, it means like if we look at what is this relative sea level that is caused by those changes, and this is during, again, those about 15 years, this is the pattern of sea level. So what do you see? Where sea level is going to be rising more? In equatorial region, okay? So, and this is a movie that shows you actually the evolution in time, and then summing up. Now, this is only for, about 10 years of data. So think about, so now it's a relatively small, effect, but we can observe it again. But if we keep losing mass at this rate, that's going to be, so it turns out that this pattern at the scale of 40 years longer is going to be the dominating pattern in defining regional sea level. Now, on top of this, of course, you have to add tides, and you have to add, storms, and you have to have all the dynamic. But think about, like I imagine there are like some people that work, in company. So if we want sea level is important, we want to do projection. Actually, at present, most of the model, all the models, they are not able to reproduce the changes that we observe. So that means that if I'm going to look at the projected sea level, usually I'm using some mean sea level. And of course, to this, I'm going to sum up what is the effect of all the, what I call the dynamic, the storm, and thermal expansion. But if I have, and then, sea level is important because if we have a house at the beach, and we're thinking how much do I have to insurance, for infrastructure. So if I want to make an estimate, and I can basically cut down by 50% my uncertainty, it's going to be a big deal for, from an economic point of view for planning. And so we're working, I think, so the great thing at UCI is that we have a very good group of people that are working in different aspects to sea level. So then again, it becomes not anymore just caring about the processes that would happen, is what are like the implication, and how do we communicate this to, the municipality and, and people. And so let me show you, this is like so here I put the sea level potential. So if I look, what is the potential? It's like how much sea level can rise because of, this is global mean sea level, because of the thermal expansion, I get up to 0.5 meter of sea level. If I push it, and I go crazy with just changing things. And how much if I melt all the glacier and ice caps? And it's about 0.5 sea level. And how much can come, again, if I melt both ice sheets? About 64 meter. So the idea is that, the message I would like to convey is that there is really a lot of potential, say potential in a good or bad way, in the ice sheet. And we're seeing those changing to be like really way more than we expected before. So why do we care about sea level? You say, well, I'm living on top of the hill in Irvine, so I'm good, even if we have 1 meter of sea level, But turns out that we're going to have major consequences, if sea level rise by, at 1 meter, that's a big deal. And so if we think about, just to make it, so this is like, and people in Florida know that very well because, they have pumping system, they have to deal with like, flooding. But this is a picture in which, this is again, Northern California. If 1 meter of sea level, we are losing SFO, and we are losing the Oakland airport. Now, that's a big deal, okay? Because, even if we live in the interior, because, Amazon now, they didn't move to New York, so we cannot order anything more on Amazon because all the headquarters are on the East Coast. Because, and then again, all the import from China, it goes, through the East Coast. And so for 1 meter of sea level, the Long Beach port is gone. Is not, so that's going to have big implication in terms of, what is the impact. And even if we don't care, even if we're on top of the hill, and it's not going to affect our houses. And again, this is the regional pattern. I think the other thing that you notice is that in the equatorial region is going to be where sea level is going to be rising more. And what, if you look at those regions, what's happening in those, so this is what I'm thinking, when I'm thinking about Europe, I'm thinking, they're complaining about immigration now, people coming, and they're coming very fast, but I'm thinking, oh, well, once sea level is gonna rise, this like very dense populated region, those people are gonna move, and they're not gonna move in the middle of the desert. They're gonna move in some nicer place. And so, it's gonna have an impact, and we wanna start thinking, because again, this is like gonna have a very big impact. And again, and the same thing for like Brazil. And so, I guess what we wanna pay attention again is that, either because we care, we think, okay, what can we do with this? And or because it's gonna affect us, and try to play both cards, depending on what people, and so, I mean, and what I would like to bring up with this is that a lot of those science questions, we go to the place in our science in which, we went from, I love the science, I love to solve the problem, but now we have to think also what we find as an impact, as an impact from making decision, and can have an impact also from, a planning point of view, and what I say to the student, I say, And don't go in panic, because things in climate, even if there is a collapse of a part of Antarctica, is happening in quite a long time. It's not like an earthquake. But this opened the door to a lot of new opportunity in terms of, like, again, technology, thinking about how we're going to solve some of those problems, in terms of their new job. They're like, it's going to have an impact in the stock market, being able to understand those changes. There's going to be an impact that's going to be new. So it's like, if you know what there is out there, you can be creative and find some exciting opportunity. Okay, so I talked to you about sea level, and now I'm going to talk to you about the last things that we do with this satellite, looking at land water hydrology. So this is like a paper that we wrote with Matt Rodell, which is a colleague of mine that work at Goddard, in India. And the movie shows you, this is a movie that showed the depletion of water in an aquifer at the border in India. This is at the border with Pakistan. And one of the great things that this satellite does, allowed to measure the mass change, so the total mass change, which means that we measure surface water, but we measure also groundwater. Now, groundwater, if we are in the US, we have plenty of wells, and you can say, if I have wells everywhere, I can have a very good understanding of what is going on with the groundwater resources. But in places where, it's hard, to measure things, it's not easy, it's very hard. So for the first time, we can use satellite data, since 2002, to measure the total water storage chain, so the groundwater in the soil. And then what we did, what this plot shows you, we used some models, so it shows you the blue line. So the black line is the signal from the satellite. The red line is the soil moisture. We use a model to estimate what is the top, the moisture for the top. And then we isolated the groundwater signal, okay? And here we have like the seasonal cycle of the different components. And we found that basically we did some calculation assuming some average, porosity for the soil, and we estimated how much is the depletion of water in this area. Well, it turns out that during the period that we looked at, the groundwater withdrawal was 20% higher than what they thought previously. And we map it in about 1 foot per year of change in the water table. Now, this is a big deal in those areas because, again, highly populated, water is very important. The other thing is that in those areas, they have a lot of crops, the rice crops, which are very high in demand. And they, we're starting, this crop, this planting has been started during the development of the well. And so people have not thought about, what is going to happen if we don't have any more water, if the aquifer don't replenish it. So this information can provide, the input to say, okay, on the long term, is this sustainable? And if it's not, being able to plan what are changes that we can make. I'm going to show you an example in the US. Okay, this is some work that we did in the US. And so when we look at water storage, well, we're in California, when, rain, this year was a good year, but if we look at, what we're interested in when we are in the drought season, because the drought impact, not just if we cannot, water our lawn, but as an impact on, again, on the economy, and on water resources. So what scientists and like to do, they use some index to measure, how is this drought? Those are called Drought Index. And here I am showing you, it's called like PDSI, which is basically the Palmer Drought Index, which is a very common index that, it was put together by a scientist, and it's putting together a lot of parameter information about precipitation, about soil, humidity, about, try to map what is the change in water in the surface. And this is like the USDM, US Drought Monitoring Index, which include also information about, local region. And, and here we came out with, we just defined a drought index based on GRACE of this satellite. So what are the difference between those droughts? So here is the comparison for, and then we have to check, does it work? I believe it, but I have to show to people that it works. And why do we need another index when we have a lot of them? And so this is a drought evolution. This is like the 2011 drought, and this is using the different drought index. So what you see, you say, oh boy, they look like they can be consistent, but this is like white is normal. It means like, and when you move to blue, it's exceptionally wet, and then we go to, exceptional drought when you go to red. So here you can see different stages, and what I'm just telling you is that PDSI and those other indexes, they don't have a lot of information about groundwater because they have mostly surface parameter. And so what you see the grays help you to track what is the subsurface water. So they have different strengths, but you can use it together to map and evaluate different stages, for example, of the drought, progression. So here is a comparison in which, we look at how similar are those, what is the correspondence between, in this case, PDSI, a GRACE drought index, and in the United States. And this is like, this is on average, okay, during, overall, one, if it's one, I mean, they meet, this like correlation, but if you don't want to think of correlation, how they correspond, I mean, they match very well. And then, again, this is all statistically significant. And we have some area where they don't look, they really look like, well, they don't agree very much. So who's right, who's wrong? And so here is, a plot. So we went to look and we went to check. And so the red time series is the GRACE PDSI and DSI, and then the black is the gray is the PDSI. And then we plot on top groundwater measurement. This we went and we found some wells, and we just look at time series of what is the groundwater change during that period, and soil moisture, which is like basically really the surface of the soil, the top few centimeters in this case. And so if you see the GRACE data, they match pretty well, with the groundwater, with the well data, okay? And the PDSI data, they match very well with the soil moisture. This tells us, like, one index gives you information that is more related to what happened at the surface. And the other one, so what happened in this period is that we had a huge heat wave. And so the drought was caused by the fact that we had this huge heat wave. And so the PDSI, the soil moisture dries very quickly, but if you look at the total water storage, it doesn't have as big an effect on there. And so you can see those two behavior. And here is like some correspondents that are very well, in Texas. And so we didn't stop to the US, and then again, so we have this, like, this is a movie, and we made this drought index. Okay, so the very nice thing is a fully observational, it's not based on model, and include uncertainty, which is a good thing to have, because then we can just evaluate risk. It's characterized, the total water storage, so we're not claiming, is the solution for everything, but is going to be, it gives you an information that you don't have, in other indices, and also include anthropogenic effects, which are very hard, to measure. And so I think the part of the work is like now that we are made, how do we make, again, people, use this information? And that's part of, our work now. And I think that even, we're thinking more and more, how do we frame this, how we convey the message, now we create product that can be used, for application. Okay, so I'm just gonna go through some conclusion. So I think that, satellite, so satellite data from mission like GRACE are really helpful to inform us about changes, on the planet. They are very important, and we understand better processes on land, but also they have implication for everyday life. The mission, informs about ice sheet and glacier change. There's, and this is an impact again on sea level, and so that we have to think about how do we, that the impact is both on population living in the coastal area, as an effect of national security and infrastructure, and in general on economy, because that's a big impact. So another thing that is important, we have information, we can use this data, and again, this is one specific satellite, but there is a myriad of information, so there is a lot of potential in trying to get this information about drought, and groundwater. And this is very important because, again, water resources are important for population, for the economic impact. crop economy, has a big impact, and food availability. And then, again, as ESS people, I do think, that it's important to study the processes. I think that it's also very important to learn how we convey this information. I think the student, how they can use this, Not everybody is going to be a professor. I think it's great, I think there are so many opportunities. And so, there are like a lot of different, and I think that, and I had, some student recently, they had to decide, I want to stay in academia or not. And I thought, well, just, it's going to be a great opportunity because we can have, provided, a company with, some, new, smart, scientist, and and again, vice versa. I told you about, remember me when you're going to be very powerful, and just maybe you and wealthy, and maybe you're going to just have some fellowship for some student. So I think it's like, but I think that anyway, and the important thing is that I do think that we have a responsibility now, that we have to really try to make sure that we can use those changes, what we understand, to make sure that we avoid the worst scenario, are prepared. And then, I do think that, UCI is a great place to just really work about this transdisciplinary, project, looking at what is the impact of those, on, the social sciences. And also, I would put also, think about technology, because, how do you measure things? Like, again, we want to measure what's the next satellite. NASA is always looking about that. And so there is a lot potential in developing new technology also in some of those research. Thank you, I'm done. So now, so what GRACE really, so we are removing actually all the non-gravitational, so what we are using really is the microwave link, is just to look at the change in distance between.
Distance follows the gravitation.
Yeah, follow the gravitation, yeah, the gravitation. So we cannot, so I think that what we are seeing mostly is like the signal, we remove all the non-gravitational pattern, what we are seeing is really mostly the signal of the mass. So when you say gravitational, well, you're meaning, you just don't mean the anomaly, you mean like the gravity.
That changes both the time and the frequency.
Yeah, so no, we're not going to appreciate those changes. I think it depends. I guess it depends. It depends where you live. If you live in a place that is going to be really affected, so you can always find the positive in things. In Greenland, the Prime Minister of Greenland in a meeting said, "Oh, climate change is the best economical opportunity for us. It's awesome. They can grow crops now. They have tourism." Yeah, it's not really, so what it is, the two satellites, so what we are measuring the change, and the position of the satellite. No, so the position, and then we convert the changes of the satellite. And then, so what we do, we upper continue the signal, and we see what is the signal. That's why we don't get very well the short wavelength, of the signal. But we have the position of the satellite, what we are measuring the change, in orbit, relative, yeah, but relative, no, what you're saying, relative to the reference system on Earth, yes. I don't know the percentage of land. It's small. The percentage of land is going to be small, So if we have to go back, so we have like 9 meters of sea level, I have to do the calculation, but relative to the total mass.
Yes, to the total mass.
Yeah, I mean, it's not, I would say it's not huge relative to the total mass. Again, 9 meters, 7 meters of sea level and 64, but the point is like, so what it is for the ice sheet, and I don't know, is that still is a lot of ice is melting, so we care because it's increased sea level. The other thing that we know about ice sheet is that they have some instability. And so they're not linear systems. At some point, so the ice flow, and depending on what is the bedrock underneath, it's going to be, it's a little bit, when ice flows on, it's a little bit like you have a ball on top of the mountain and you push the ball, and then the ball rolls down, and it can roll down faster or slower, than if I don't touch it, even if I don't do anything, the ball keeps rolling. Now, depending on, if I have a very paved street, or I have like a street with some high bump, the ball can, slow down, or can stop eventually if I have a big mountain, at the end. And so how the bedrock underneath the ice sheets, what is like, and how, different forces that has an impact, or how fast those glaciers. And what we find that a lot of those glaciers, and this is like both in, so this is the area, for example, in West Antarctica, we don't have any more bump, and they're going fast. So what happened is that they could accelerate the speed up a lot. And so that may, even if it's more, again, it's more percentage, there is this area, the red area that, you saw in the Amundsen Sea sector, in West Antarctica alone, could raise sea level by a meter, itself. So, that's, and those instabilities. So I think that what we want to worry is that I don't think we should go in panic, but we have to be, conscious about the fact that things can happen faster than we expect. We don't need a huge portion of the ice sheet to melt to make a big difference. And you're right that, the coastal area now, is a small percentage, but then again, because our highly populated region, or because, sometimes I look at the coast and I like, people, I look and I visit like these beautiful houses, in Laguna Beach, and I'm thinking, in Italy, you always give your house to your kids, so I have that, and then it's always very hard to sell a house, like the, the one in the, I have the house that's to my grandmother, and it's like nobody goes, and I'm thinking, well, if people do this here, I don't know what is going to come to your, great-grandchildren, because the sea level is going to rise and it's going to get closer. So it's all relative, but, and I don't, again, it's not like, I think I already take it as an opportunity, how we plan. We have all the means to plan, to change things, building codes, our plan, building new building codes at the scale of 40 years, they're relevant. So it's good to have in the back of our mind to say, okay, can I do the best job accounting for this? I think it's going to be tough, but it's worth thinking now. This like a cube satellite, which we can put like you need to have we're not quite there, but I think maybe eventually. I think eventually what we want to do, we're going to have a couple of satellites in orbit, because now what we have, the satellite is almost in a polar orbit. That means that I get a map of the entire gravity field. I have just a very tiny hole, where I don't see things at the poles. But really what happened is that because I have a mean field, every signal, like shorter than a month, is going to have an effect. It's going to have an error because I have to average out. We are removing it. And so to really beat down the spatial scale is like, and that's why I actually like this field, because you do work and thinking, how do we solve this problem? It's technology to do better measurement. You would need a pair of satellites, because one in a lower orbit and one in a almost polar orbit. And I don't think we're quite there with making those cube satellites, but I think that eventually, to me, it's like that's, we had the first mission, it was the first time. The second one was just launched, is still, the decadal survey, which is a big assessment that the National Academy of Science does, put GRACE 2 mission as one of the priority, because it really provides a unique information. And it can have a lot of application if you can go down to smaller scale.
Thank you very much, Professor Velicogna.